is Dr. Tishan. In this video, we're going to take a look at a theorem that you learned in Calculus 1, the second derivative test. The second derivative test helps us determine if your critical numbers of a function are local maximums or local minimums. So on the screen over here, we have the theorem, the second derivative test. We'll just talk through it really quick and we'll do two examples. Also, you see we have the first derivative test, so we're going to review the first derivative test as well. So first derivative test and second derivative test, they're going to tell us if our critical numbers are local extrema of a function. Your first derivative test, okay, you're going to find your critical numbers, and once you find your critical numbers, we usually make a chart. We're going to take the critical number, and your first derivative test says wherever your critical number is, if your numbers before the critical number, if the derivative values are positive and they change from positive over to negative on the other side of the critical number, then your critical number is a local maximum. And then if you're testing your critical number, the first derivative test, values on the left go from negative to positive, you found a local minimum. So that's your first derivative test in terms of finding local extrema. Your second derivative test, what we do with the second derivative test is we take the critical number and we substitute it straight into the second derivative. When you plug the critical number into the second derivative, if the value you get comes out negative, your critical number is a maximum. And if your value, plug in the critical number to the second derivative, if the value comes out positive, then your critical number is a local minimum. Now with the second derivative test, what if the value comes out equal to 0? Well, if the value does come out equal to 0, then the test is inconclusive and you just have to go and use the first derivative test, which is why we probably need to review it in this video as well with the second derivative test. So let's take a look at, we're going to do two examples, okay? So let's take a look at the first example. We're doing two polynomial examples. Our first example, we are going to take the function x to the third power minus 6x squared plus 15. All right, so we want to determine where the local extrema, where the local max, where the local min is. Let's start by, let's find our first derivative. We'll use the first derivative test first, and then we'll look at the second derivative test. You can see how they both work. So your first derivative, so let's go ahead and write the first derivative of this function. The first derivative, using the power rule, the derivative of x to the third is going to be 3 times x squared. All right, minus, use the power rule, bring the 2 around front, times 6, so you have 12x to the first, and the derivative of a constant is 0. So here's our first derivative. Let's go ahead and get our critical numbers. So our critical numbers, what we're going to do is we're going to take our first derivative, 3x squared, all right, minus 12x, and we're going to find the zeros, okay? So let's figure out where this is equal to 0. Now you have a quadratic, so to find the zeros of a quadratic, we are going to factor. So let's factor out a 3x, okay? And so factor out a 3x, you have an x left over here. When you take out a 3 and an x here, minus 4, all right? So our critical numbers are going to be 0, and they're going to be 4. There's the zeros of our derivative, okay? And these are your critical numbers. These are our critical numbers. Okay, so let's go ahead and determine these critical numbers. Are they maximums or minimums of our function? Let's use the first derivative test, okay? So the first derivative test will make a chart. Let's go from negative infinity to 0. We want to make a chart, 0 to 4 and 4 to infinity. Okay, so I'm setting up some intervals to represent my number line. Okay, so negative infinity to infinity, setting up some intervals to represent my number line from negative infinity to infinity, and I'm breaking them off at my critical numbers, okay, in order, in chronological order. So negative infinity to 0, 0 to 4, 4 to infinity. Now what do I want to do with these intervals? I'm going to take a number from these intervals, any number I want from these intervals, and I'm going to plug them into my first derivative. And I think I'm going to plug them into my factored form of my first derivative. I can probably see it better. So I need any number between negative infinity and 0. So I'm going to just pick a test value, anything you want to use. Maybe I'm going to use negative 1. So when I plug in negative 1, I get negative 3 times a negative 5. Well, that's a positive 15. I don't need the value, I just need the sign, okay? What about between 0 and 4? Let me pick a number between 0 and 4. Choose 1, choose 2, choose 3, anything you want. I'll choose positive 1. Choose positive 1, that gives me a positive 3 times a negative 3. Well, that's negative 9, but it's a negative, so I just need the sign. Pick a number greater than 4, 4 to infinity. Any number you want in this interval, infinitely many numbers. Pick anything you want. I'm going to pick 5. When I plug in 5, 3 times 5, 15, and 5 minus 1, 5 minus 4 is 1, so 15 times 1, it gives me a positive number, okay? So your first derivative test says, okay, around your critical number, when the derivative changes from positive to negative, then this critical number, x equals 0, this critical number is a local maximum, all right? So this is what we have here. So x equals 0 is our local maximum, the x coordinate of the local maximum. All right, when your first derivative changes from negative to positive, and you can see where the chart pivots on x equals 4, so when your first derivative changes negative to positive, you found a local minimum, okay? So for this function, and these are the x coordinates, you can plug back into the function to get the y coordinates, but the x coordinate of the local maximum is x equals 0. The x coordinate of the local minimum is x equals 4. Using your first derivative test to find the hills and valleys of your polynomial function. All right. There's another way to determine this. There's another way, and that's the second derivative test. So what does the second derivative test say? Okay, well the second derivative test says let's go ahead and find this second derivative of our function. So we'll find the second. The first derivative is right here, 3x squared minus 12x. So let's find this second derivative. Second derivative using the power rule, bring the 2 around front times 3, that gives us 6 times x, okay? And then the derivative of 12 times x to the first is just going to be 12. Here is our second derivative, okay? This second derivative test says you're going to take the second derivative, and you're going to plug in your critical numbers. We're going to take the second derivative and substitute in the critical numbers to the second derivative. Take the second derivative, we're going to plug in 0 and plug in 4 because our critical numbers here are 0 and 4. So we're going to plug in our critical numbers to the second derivative. All right, so plug critical numbers into the second derivative. When you plug in 0, 6 times 0 minus 12 is a negative 12. When you plug in the critical number to the second derivative, if the value comes out negative, then the critical number is a local maximum. So x equals 0 is a local maximum. All right? All right, let's plug in 4. So we're going to have 6 times 4 minus 12. 6 times 4 is 24. 24 minus 12 is 12. That's positive. When you plug your critical number into the second derivative, if the value comes out positive, your critical number is a local minimum. This value is positive greater than 0, so x equals 4 is going to be a local minimum. All right? So, and you can see first, whether you use the first derivative test or you use the second derivative test, your solution's the same, okay? So your first derivative test, find your first derivative, okay? All right, find the zeros of the first derivative to get your critical numbers. All right, once you have your critical numbers, you set up a chart. Negative infinity to infinity and break it off at your critical numbers in chronological order, set up your intervals, all right? All right, and then each of the intervals, pick a test value in each interval. Pick a test value, plug it into the first derivative. Value comes, so it's positive, value comes out negative, just put it in your chart, all right? Then once you're done completing your chart, read your chart, okay? So your first derivative, it's a theorem, your calculus theorem. The first derivative test says when your derivative changes from positive to negative, that means your function is increasing to decreasing, okay? You have a local maximum, right? When your derivative changes negative to positive, right? That means that your function is decreasing to increasing. You have a local minimum, all right? So that's one way to figure out if your critical numbers are local extrema. We have a second way, all right? The second way to see if your critical numbers are local extrema right here is take your critical number, plug it into the second derivative test. It's your second derivative test, theorem in the book, okay? When you plug a critical number into the second derivative, if the value comes out positive, your critical number is a minimum. If the value comes out negative, your critical number is a maximum. So we plugged in our critical numbers, 0 and 4, into the second derivative. We plugged in 0, value came out negative, critical number was maximum, right? We plugged in 4, value came out positive, that critical number is a minimum, and you can see that whichever method you choose to first derivative test, second derivative test, they both work, all right? Now, second derivative test might be a little bit shorter, all right? But sometimes the second derivative test, what if the value equals 0? Okay, when you take and use a second derivative test, if the value is equal to 0, the test is inconclusive and it doesn't work. All right, if this value equals 0, well, you may still have a local extrema. You might have a local max, local min. All right, if your value comes out equal to 0 with the second derivative test, it means the test didn't work. So that means you're going to have to use the first derivative test. All right, and this always works. Okay, let's look at another example. Okay, so I'm going to erase this one and let's look at another example, a little bit more involved of an example, but I want to do an example where the second derivative test generates a value equal to 0. Okay, so I want to show you that if the value does equal 0, you're going to have to make a chart and you can still have an extrema. So we're going to take a look, but it's a more involved example. If you need another example and you want to see the second derivative test when you do have an inconclusive with a polynomial function. So let's take a look at one of those right now. Okay, so this will be our example number 2. So our example number 2, and let's go ahead and we'll use the second derivative test first, okay, to find our extrema. So here's our example number 2. So our function is going to be, let's see, for this one we're going to use x to the 4th times the quantity x minus 1, that quantity is cubed, okay? So we're going to use this, all right? So let's go ahead and let's find our first derivative. So now for the first derivative, we've got some work to do with this, right? So we're going to have to use the product rule with a chain rule inside a product rule, okay? So this is a busier one, but this is going to give you a good example of the when you see inconclusive for the second derivative. So we're going to use the product rule, so I'm going to bring that x to the 4th down, okay, times the derivative in here, so it's 3 times x minus 1 to the second power chain rule, and the derivative of the inside is just 1, isn't it, okay? Plus, I'm going to bring that second expression, x minus 1 quantity cubed, I'll bring that down, and that gets multiplied by the derivative, and here the first term, which is 4x to the 3rd. So here is, and now let me just clean this up and simplify this a little bit. Okay, we want to write this as one term actually, because we need to find our extrema. So if we look at these two terms, and I know there's a lot of grouping symbols involved, but if you look at these two terms, what do we have in common, okay? I think we have an x to the 3rd power in common, all right? And we have x minus 1, okay? So we have x minus 1 quantity squared. That looks like it's common to both. All right, and so what do we have left over when we take that out? So we're going to take out both of those and one of those. So you have a 3x on the first term left over, okay? All right, and then the second term, you take out the x to the 3rd power, so you have a 4 left over, and we're only taking 2 of those out, so you have an x minus 1 left over, all right? So one more step so what do we have here? Well, one more step to kind of simplify this. We have x to the 3rd, and we have x minus 1 quantity squared. Now what do we have in here? 3x plus 4x, right? I need to distribute the 4, so I have 7x, okay? Distribute the 4, so minus 4, all right? So we're looking at this right here, all right? Now, where are my critical numbers? Well, this is a polynomial function, so my critical numbers will take place when this polynomial function equals 0. Let me just write out my critical numbers right now. So critical numbers for this problem, all right, are going to be, let's see, they're going to be at x equals 0. Do you see that? So x equals 0, x equals 1, and x equals 4/7. Okay, so this is the value that we're going to end up with. Okay, so here's the value right here. These are the values. This is our critical numbers right here. All right. Now, are they local max, local min? Neither. What are they? Okay. How do we classify them? Well, when you've got your critical numbers, we want to know if they're local extrema. 2 ways to do it. Okay. So you could make your chart and check the sign positive to negative. All right. Or you could use the second derivative test. Let's go ahead and get the second derivative. All right. Let's use the second derivative test first on this one. All right. Let's see. So what do we have? Well, bring the first. So x to the 3rd. All right, x minus 1 squared times 7. I'm going to use, to get the derivative, I'm going to use a product rule, okay? But I've got 3 terms, and so I'm going to take the first term, second term derivative of the 3rd. I'm going to add to that the first term, third term derivative of the 2nd. Then I'm going to add to that the second term, third term derivative of the 1st. I'm going to use just like a product rule for a triple. So we did the first, the second, the derivative of the 3rd. Okay, now I'm going to do the first term, x to the 3rd. The 3rd term, 7x minus 4. And I'm going to take the derivative of the 2nd, which is going to be 2, quantity x minus 1, to the 1st times 1 using that chain rule. okay? All right, and then I'm going to take, what do I need to do here? The second term and the third term, so x minus 1 quantity squared. The third term, 7x minus 4, times the derivative of the first, which would be 3x squared. So it looks like we're here, okay? And let's go ahead and take our second derivative, and let's try to simplify this. Okay, so let's go ahead and we'll try to simplify this, okay? Let me just kind of see what I have here. I have 7, and I have x cubed, and I have x minus 1 squared for the first term, all right? What's going on here? I have a 2x cubed. All right, I have an x minus 1, and I have 7x minus 4. And I have 3x squared. I have x minus 1 quantity squared, and I have 7x minus 4 here. All right? So what can we take out of each of these terms? Let's factor something out so we can make it a little bit easier to substitute our numbers in. So looking at each of these three terms, 7, a 2, and a 3. Nothing common there, but looks like we can take out an x squared. All right? What about the x minus 1 factors? You got 2 here, and 1 here, and 2 here. Looks like we can take out an x minus 1. All right, it looks like that's all we can take out. So let's do that for each of these terms, okay? So you take out 2 of those 3 x's, you have an x left over. So we've got the 7, we have an x, and we have x minus 1 left over from the first term, all right? The second term, you're taking out the x squared, so we have the 2, and we still have an x. We're taking out the x minus 1, but we have 7x minus 4, all right? And the third term, you're taking out the x squared, so you still have the 3. We're taking out one of those 2x minus 1s. All right, and then we're taking out is 7x minus 4, all right? So this is what we have when we factor out, all right? Now let's go ahead and bring down the x squared, okay? And bring down the x minus 1, all right? And then let's go ahead and distribute and combine everything inside in the bracket here. So distribute the 7x, the 7x squared minus 7x, all right? And then over here, distribute the 2x in here, so positive 14 x squared, and then 2 times negative 4, so there's a minus 8x here. Now we're going to have to distribute here and distribute the 3 after we actually expand this two binomials to a trinomial. So we're going to try to do all that at once. So there's your 7 x squared times 3. So that gives us a positive 21x squared for your first term. Minus 4x minus 7x. So minus 11x times 3. So minus 33x, okay? And then negative 4 times negative 1, positive 4, but multiply that by 3, and so you end up with 12, okay? And I think I said minus 33x here, right? So minus 33x, and then positive 12. So here's what you end up with when you expand this. Now, let's go one more step here, and let's just combine what's in that bracket. So out here, we're trying to factor this up, just to make it a little bit easier to plug our critical numbers in, all right? Because this is a pretty long second derivative. How many x squareds do we have? 7 plus 14, that's 21. 21x squared and another 21x squared. We've got 42 of them. There's 42x squareds, okay? How many x's? Negative 7 and negative 8 is a negative 15x, and negative 15x minus 33x, it's minus 48x. All right, and then what do we have here for the constants? We just have the positive 12. We have the positive 12, all right? So here's our second derivative. We can actually take and factor a 6 out. I'm out of space down here, but let's just travel, okay? All right, so let's travel. So now what's our second derivative looking like, okay? So our second derivative, let's factor a 6 out of this term here. So we'll call this up front 6x squared, and you have the x minus 1. We're going to take a 6 goes into 42, so this is going to give us what, 7x squared, okay? 6 goes into 40 minus 8x, all right? And then 6 goes into 12 twice, okay? So here is our second derivative. All simplified, this is our second derivative. What do we want to do with our second derivative, okay? We want to plug in our critical numbers. Remember what we're doing here is we're going to take our critical numbers, plug them into the second derivative, because we want to know if our critical numbers are indeed local extrema or not local extrema. So we're going to take our second derivative, we're going to plug in 0. We're going to take our second derivative, we're going to plug in 1. We're going to take our second derivative, and we're going to plug in 4 over 7. All right, so we're going to plug in these values, okay? So when you take your second derivative and you plug in 0, you get 0, okay? You get 0 times negative 1 times 2, right? So you get 0 for this term times negative 1 times 2. You get 0, okay? So inconclusive. So is this a max or min? We don't know. It's inconclusive. Let's plug in 1. When we plug in 1, we get 6. Okay, so we get 6 here times 1 minus 1, that's 0. And then when you plug in 1 here, 7 minus 8 is a negative 1. Negative 1 plus 2 is 1. So you get 0, because 0 times anything, you could probably see you get 0. Okay, plug in 4 sevenths and you're going to get 6 times 4 sevenths. Okay, so you're going to get a positive number there. 4 sevenths minus 1 is a negative number there. Okay, and then let's see, 4 sevenths times, so well, you're squaring 4 sevenths. Okay, so one of the fractions there cancels, so that's a fraction minus 8 times 4 sevenths plus 2. That's going to give me a negative number there as well. So this is a positive number. Whatever the value is, it's a positive number. Okay, positive number. So what does that mean that we have? So if your second derivative, plug it into the function, if the second derivative comes out positive, okay, comes out positive, then x equals 4 sevenths is a local min. Okay, so x equals 4 sevenths, we got that. That is a local minimum. We know that's a local minimum. All right, what's happening over here with x equals 0 and x equals 1 though? Okay, what's happening here is our second derivative test, all right, is inconclusive. It's inconclusive. So what do we do if it's inconclusive? You got to use the first derivative test. You got to go and make a chart. All right, so let's use the first derivative test. We're going to make a chart. So we're going to go from negative infinity, all right, to 0. We're going to have to consider 0 to 4 sevenths, so we pick the right numbers. Okay, 4 sevenths to 1 and 1 to infinity. Okay, so we're going to have to make a chart. We're going to make a chart, and we're going to check the numbers in the first derivative. All right, so we don't have to check at 4 sevenths though, because we know x equals 4 sevenths is a local minimum. All right, so we know that this is a local minimum. All right, so we don't have to check there. We don't have to check here, but we do have to see what's happening at 0. We do have to see what's happening at 1. All right, so if you take your critical numbers, you plug them into your second derivative. All right, the value comes out positive, critical numbers a minimum. All right, value comes out negative, critical number is a local maximum. If the value comes out equal to 0, the test doesn't work. You're going to have to go back and use the first derivative test to see if truly you have a local extrema or not. Let's go ahead and do this. So the first derivative, where is our first derivative? It's back over here. I'm going to use this one. Okay, now this middle term here we're squaring, so we know that's always positive. So I just have to consider, so I want to plug in a number less than 0, say negative 1. If I plug in negative 1, that's going to be a negative, that's going to be a positive. 7 times negative 1 is negative, so that's going to be a negative. So negative times negative. My value for the first derivative will come out positive here. Between 0 and 4 sevenths, I'm just going to consider 0.1 here. Okay, so 1/10. 0.1, when I cube it, that's going to be positive. That's going to be positive. 7 times 0.1 is 0.7. 0.7 minus 4 is negative. Positive times negative. Okay. All right, and then let's go ahead and pick a number between 4 sevenths and 1. I'm going to pick 0.9. Just consider 0.9. Cube it, it's going to be positive. Take 0.9 and take it in square quantity. It's going to be positive times positive. 7 times 0.9. 7 times 9 is 6.3. 6.3, that's positive also. Okay. Between 1 and infinity, plug in 2, and that's going to give you a positive times 14 minus 4 positive. So you're positive here. Okay, so what about our local extrema? Well, at x equals 0 and x equals 0, okay, we are changing from positive to negative. It is a local max. We have a local maximum at x equals 0. The second derivative test did not indicate that, but it truly is a local maximum. All right, what about at x equals 1? X equals 1, we have neither. All right, local max or min at x equals 1. We have neither. There's neither at this spot here. All right, so this was a busier example. If you followed this through, this was a much busier example. All right, so your second derivative test, you're going to plug your critical number into the second derivative. If the value you get comes out positive, your critical number is a local minimum. If the value you get comes out negative, your critical number is a local maximum. If the value you get comes out to equal 0, then the test doesn't work. Maybe it still is a local maximum or local minimum. Maybe it's not a local maximum or local minimum, and you have to investigate that to see. So sometimes with these busier problems, just be really careful, all right? Okay, whew. All right, so I hope that gives you everything you wanted with the second derivative test. So thank you so much for tuning in, and if these videos do help, I would appreciate if you would subscribe. So thank you again. Take care. Bye-bye.